Welcome to this section on training and optimization. After looking at the loss, in the next section they present a theoretical analysis of adversarial nets. And when given enough capacity, we are able to produce a data generating distribution G, which is very similar to D. Optimizing D to completion in the inner loop of training is computationally prohibitive, and on finite data sets would result in overfitting. Instead, we alternate between k steps of optimizing D and one step of optimizing G. This results in D being maintained near its optimal solution, so long as G changes slowly enough. The procedure is formally presented in algorithm 1. And in practice, equation 1, which is this, may not provide sufficient gradient for G to learn well. Early in learning, when G is poor, D can reject samples with high confidence because they are clearly different from the training data. In this case, the log of 1 minus dg saturates. Rather than training G to minimize the log of 1 minus dg, we can train G to maximize the log of dg. This objective function results in the same fixed point of dynamics of G and D, but provides much stronger gradients early in learning. Now, if we look at this figure 1, we have the generative adversarial nets, which have been trained by simultaneously updating the discriminator distribution, which is in blue, so that it discriminates from samples from the data generating distribution, that's in black. So here we have the real data, and with this blue, we see clearly that those from the real data, or most values from the real data, are considered to be ones, while most values from this green, that's the generated data, are considered to be zeros. So we have this high with the blue and then the low with the blue. Then the upward arrows show the mapping, or show how the mapping x equals g of z imposes the non-uniform distribution pg on the transformed samples. G contracts in regions of high density and expands in regions of low density of G. Now if we look at this first one, that's the A, we have an adversarial pair near convergence. We have that PG is similar to P data and D is a partially accurate classifier. That's what we have here. Then the B, in the inner loop of the algorithm, D is trained to determine samples from data converging to D star. Now D star is like D optimal. So this is the optimal value for D for a given G, and it's given as P data divided by P data plus PG. We shall look at this later on. Now for the C, after an update to G, gradients of D has guided G to flow to regions that are more likely to be classified as data. So this point is very important, as once the D has been trained, and now during the update of G, this gradient from D actually help the G in flowing to the right directions. Now, after several steps of training, if G and D have enough capacity, they will reach a point at which both cannot improve because PG equals P data. And at this point, we see clearly how this blue line doesn't even know the difference between the P data and the PG, as they both are the same now. And this is the aim of our task. Now the discriminator is unable to differentiate between the two distributions, so we have dx equals a half, whether the x is from the distribution PG or distribution P data. So right here we have the algorithm. We select many batches of M noise, many batches of M examples. We update the discriminator by ascending stochastic gradient, since we're looking for, or we're maximizing the loss, and then we do this for k steps. So we train the discriminator for k steps, and then we sample many batches of M noise samples. So this is for the discriminator, and then now is for the generator. We now update the generator by minimizing the loss. So this is how the original GAN algorithm was built. Now let's look at some other important points to note, like the fact that for a fixed G, the optimal discriminator D is this p data of x divided by p data of x plus pg of x. We shall look quickly at the proof. We recall that the training criterion for the discriminator d given any generator g is to maximize this quantity VGD. This quantity has been defined already, so we have VDG right here defined as such. We've seen this already, and from the expectance formula we could transform this into an integral. We recall that this formula is given as a of x, as the expectance of x is equals the integral of x f of x. So right, that's how we obtain the integral of p data of x log of d of x plus the integral of p z log of 1 minus dg. And then we write this first part, while this now turns into the pg of x log of 1 minus d of x dx. So since now we're having dx, we could combine this as one integral. Note that this p data is the distribution of real data and pg the distribution of fake data. Then the others have here that for ab, element of r square, considering that a is different from 0 and b also different from 0, this function achieves a maximum at a divided by a plus b, considering that we fall in the range 0, 1. Now let's understand exactly how we come about that. Supposing we have this f of y equals a log y plus b log 1 minus y, then f prime of y equals 0 will imply that a on y minus b on 1 minus y equals 0. Now the reason why we're talking about this is because at maximum points we actually have the first derivative to be equal to 0. So we're trying to actually do the first derivative test right here, and then this implies that we could derive this and equate it to 0. Now deriving this with respect to y, a is considered to be a constant, so we have a as a constant, and then the log of y, the derivative of the log of y is 1 on y, so that's why we have a on y, and the derivative of 1 minus or log of 1 minus y is the derivative of 1 minus y, which is minus 1 divided by 1 minus y, so that's why we have a negative here. And then we have b, the constant, which is now equals 0. So all this equals 0. And then if we rearrange this, we have that y equals a on a plus b, while we note that a plus b is different from 0. Now we're sure that this is a turning point, but it could be a minimum turning point instead of a maximum turning point. So to test to know whether it's a minimum or maximum turning point, we have the second derivative test, where we have f double prime of this value at the turning point, which when we compute, we actually see it as less than 0. And with that, we understand why, or the others say, yeah, we have a maximum in 0, 1 at a divided by a plus b. So this tells us that the maximum of this function right here is this p data divided by p data plus pg, where this p data is a, pg is b. This is considered to be the y we had here, and then this is the 1 minus y. So with this, we could see clearly how we obtain this. Now the training objective for D can be interpreted as maximizing the log likelihood for estimating the conditional probability p of y given x, where y indicates whether x comes from p data or from pg. The minimax game in equation 1 can now be reformulated. So this is the game we're trying to solve initially. Note that we're doing this for the discriminator, and we could modify it such that since the max of VGD is our optimal value for the loss, then we have seen clearly from here that we could always replace this D with the optimal value for D. That's the value of D, which will make all this to get its maximum. And with that, we call it DG star, which is DG optimal. Now we have this log D of X, or D star of X, plus log 1 minus D star of G. Then we write this again. We have this plus this. Now notice how we live from X to G right here. And then replacing this dg star by this value. Actually, because of this a on a plus b, we now obtain the log of this plus the log of pg on p data plus pg of x. Now, looking at theorem 1, it said that the global minimum of the virtual training criterion, that's C of G, is achieved if and only if PG equals P data. So actually, this is, in this case, since we're dealing with GANs, our global minimum, because our aim is to make sure the fake data resembles as much as possible as the real data. And at that point, C of G achieves the value of negative log 4. So we shall prove this quickly. We see that PG equals P data when the G star equals a half. Now, if we take a look at this equation right here, that's this one right here, we see that when P data equals PG, so let's suppose this P data equals PG, we have PG divided by PG plus PG, and obviously that's PG divided by 2PG, and that's a half. So that's exactly why this is set right here. And hence, by inspecting equation 4, that is taking this equation right here and replacing this with a half, we see clearly that we have the log of a half plus the log of a half. And so clearly we see that at the points where we have our global minimum, CG achieves the value of negative log 4, because log of a half plus the log of a half is equals the negative log of 4. Since log of a half is log of 2 to the negative 1, and log of 2 to the negative 1 is negative log of 2. So that's what we have here. And then we also have this negative log of 2, which gives us this plus this, now gives us negative log of 4. The authors of the paper had reformulated CG to be negative log of 4 plus the KL, that is a Kullback-Leibler divergence of P data with P data plus PG divided by 2 plus the KL divergence of PG with P data plus PG divided by 2. Now we shall try to show how they came out with our expression. So we have CG, which is equals the integral over x of P data log of P data divided by PG plus P data plus PG log of PG divided by PG plus P data. And this is gotten from this expression where we had CG to be the expectance of the log of P data divided by P data plus PG plus expectance of log of PG divided by P data plus PG, where the expectance here was over x, which is from the distribution P data, and here x distribution PG. So that is why right here we have P data x times this plus PG x times this. So it's just like x f of x plus x f of x. Now we could decide to add 0 to this. So that's basically what they did. We have log 2 minus log 2, which is a 0, log 2 minus log 2, which is a 0. So we haven't changed this original equation. Now that that's done, we can rewrite this. Notice that here we had P data and here we have PG. So we regroup the PG and P data for the negative log 2. Negative log 2 P data minus log 2 or plus negative log 2 PG. If you combine the negative log 2, you have negative log 2 P data or PG plus P data, which is getting from this and then this combined. Now we add again the parts which contain P data separately and the parts which contain PG separately. Here's the parts which contain P data. We have this, and then we have plus log 2 times P data. So here we have log 2 plus this expression here, all of this times P data plus the PGs, the log of this plus log 2, all of that times PG. So we have this combined. We recall that from the definition of a probability distribution, we have that the integral of f of x dx is equals 1. So that's why we have this integral of PG of x dx 1 and that of P data 1. So this gives us minus log 2 integral of 2 dx. Now at this point, we shall look at the KL divergence definition. The KL divergence of p with q is the integral of p of x log of p of x divided by q of x dx. So this is his definition right here. And this mathematical expression actually shows us how different these two are. Or in general, it shows how different two probability distributions are. Now we have the KL divergence. We could also rewrite it as the expectance of log of p divided by q, where x is taken from the distribution p. Now we have the DKL, that's the KL divergence of p data with p data plus pg divided by 2. Following this will be given as the expectance of x from p data log of 2 p data divided by p data plus pg, and also this divergence of pg with p data plus pg divided by 2 to be expectance of log of 2 pg divided by p data plus pg. Now this is gotten, we could see clearly how it's gotten from this. We just basically take this divided by this. So once we see this, you notice something right here. We notice that this is the expectance, or this is this right here. So this is the expectance of log of 2 p data divided by p data plus pg, which is basically this, where x is taken from p data. So if x taken from p data, we could rewrite it like this integral right here, and then plus this other part, which is basically this. And with that, we could say this equals negative log of 4, because we have 2 right here. Negative 2 log 2 is the same as negative log 4, plus the KL divergence of p data with p data plus pg divided by 2, plus the KL divergence of pg plus or with p data plus pg divided by 2. The authors also have defined this C of G in terms of the Jensen-Shannon divergence, which is what we get here, the GSD, where we have the C of G equals negative log 4 plus 2 times the Jensen-Shannon of p data with pg. Now the definition of the Jensen-Shannon is given as GS of p with q equals half the KL divergence of p with m plus half of the KL divergence of q with m. So notice we have pq, we have pq right here, but this is p with another distribution m, and then this is q with another distribution m. So right here we simply could see from here that if we have here, for example, this is our p data and then this is our m, so we have p, or rather this is our p, our big P, as we could see from here, with m, plus this our big Q with m. So if we look at it like way, we could see clearly that this gives us the Jensen-Shannon of p data with pg. So that's what we get here. Now we multiply by 2 because these halves are taken off. So to take off these halves, we multiply by 2. So that's exactly what we get in the paper. And then finally, for this last proposition, we have that if G and D have enough capacity, and at each step of algorithm 1, the discriminator is allowed to reach its optimum given G and PG is updated so as to improve the criterion. This, where this is actually our criterion, then PG converges to P data. We can now define the optimizer, which is Adam. We will take this off. So we have the tf.keras.optimizers right here. We're gonna have this. So from TensorFlow .keras optimizers, we import Adam. Then we move on to the next. Then we define the number of epochs we're going to be working with. We have, say, 100 epochs. Then we have the train step. We have this to use the graph mode while training. We have the noise, which is generated right here. And then the gradient tape for the generator and the discriminator. With this, we generate the images using the noise we had declared right here. We're in train mode. We have the generator model, and then once we generate this image, we have actually created the fake images actually. So we have the real output, which when it passes through the discriminator model, which is actually the image. So because the image gets into this, so we have the image, that's the actual real images, which pass through the discriminator model, which produces the real output, while the generated images coming from the noise, which pass through the discriminator model, producing the fake output. We then get into the G loss, which is the generator loss, which takes in the fake output, while the discriminator loss takes in the real output and the fake output. After doing this, we compute the gradients. So here we have the generator gradients, and then we have the discriminator gradients. For the generator gradients, we have the generator tape, which we had defined earlier here. The gradient of the loss, that's the G loss, with respect to all the generator parameters which are trainable. And then with the discriminator, we have the gradient of the loss with respect to the discriminator model parameters which are trainable. Once this is done, we now optimize our generator and the discriminator using the gradients and the model parameters. Then we return the discriminator and the generator loss. So with this, we've defined a training step, and we could go ahead to define the train function. Here we have the train function, which takes in the data set, takes in the number of epochs. So for each epoch, basically this training step is, we're supposing one epoch. So for one epoch, for each epoch in the range of epochs, we take an image, we pass it, or we train that image with us, the image batch, the batch of images we're working with for each batch. We have this, and then we get a discriminator and generator loss, which is getting from here. We plot out the image. Now the reason why we're plotting out the image is so that we see exactly how our model evolves in being able to create the fake images. So that's why we do this plot. We show that plot, and then we print out the values for the D loss and the G loss for each epoch. So that's it. Then yeah, we could just have a train of the data set while taking in the number of epochs. We now run the train. Then after some time, we could see how the model is struggling to create this fake images. We see from the first epoch we have this image, then we move to the next, we see we get this image. You see it starts, that leaves from here where, and then it gets to this point where it starts figuring out that human images or human faces take this kind of form. We move to the next, you see it starts to create better images, then to the next, then to this, and then this is what we get at the seed epoch. So here we have the D loss 0.75 and then the G loss 2.19. Also notice how the D loss and the G loss values are fluctuating, and also that the D loss is actually decreasing while fluctuating, and then the G loss is increasing also while fluctuating. And with this, you could keep on training to have better images. Now we could also replicate this kind of results with the MNIST data set. So let's have this. We have the MNIST data set right here. We get the training images. We have the new input dimension, which is 28 instead of 64. The batch size defined. We divide this by 255. We have the data set that's created. And then right here, we modify this. We leave from 3 to 1. So that's why we have this. You see, it ends with 28, 28, 21. And then here we start with 1. So instead of 3. So here we have this. We train, optimize. And then here are the kind of results we obtain. We see initially it starts struggling, and then it starts creating this kind of values. You see now it creates this 3 quite well. See the kind of values it creates as we go on with training. Then for this last epoch, for this other epoch, we have this. Now notice that actually what happens is initially you see there was no major difference between the this yellow spots and then this blue spots. Note that the blue spots, a typical blue spot should be a 0 value, and then this very yellow spot should be a 1. So the difference between this and this isn't very clear at the beginning. You see this point here, which is kind of like yellowish everywhere. See, and then as time goes on, it starts to differentiate quite well. You see, it starts to show a great difference between this part and then this part as it starts to learn better.